Good evening, students. Welcome to day 14 POC-II crash course. So in today's session, I'll be discussing about chemistry of anthracene. In yesterday's session, I have discussed about chemistry of naphthalene, where I explained about resonance, isomerism, Haworth synthesis, and various reactions of naphthalene, along with the uses and structures of naphthalene derivatives. So if you have missed yesterday's session, then a replay will be available, so you can watch it. So if you have any doubts related to naphthalene chemistry, then a WhatsApp group link will be available in the description of that replay. So you can join in that WhatsApp group and you can clarify your doubts. Now in today's session also, throughout the session, if you have any doubts, you can type your doubts in chat. Quiz will be enabled at the end of this session. So soon after this session, review the concept for about 10 to 15 minutes, then attempt the quiz. Now without wasting much of your time, let me start. First, I'll be explaining about resonance phenomena. If you're watching replay of this particular session, then better you complete the replay of the naphthalene first, okay? Because once you understand how many resonance structures are possible for naphthalene and how to write those resonance structures, then it becomes easy for you to understand even in case of anthracene also. Okay, now let me share my screen to explain about resonance phenomena in anthracene. This is the structure of anthracene. For the convenience purpose, to differentiate the three aromatic rings present in anthracene, they are labeled as 1, 2, 3 ring systems. Anthracene, it consists of linear fusion of three aromatic ring systems. The linkage between two aromatic ring systems present in anthracene is considered as linear fusion or orthofusion. That means one benzene ring is attached to another benzene ring by using two adjacent carbon atoms. So this kind of fusion is known as linear fusion or orthofusion. The molecular formula of anthracene is C14H10. And it is also like naphthalene, it is obtained from coal tar and petroleum. And it can also be synthesized by various other methods, which I will be discussing under synthesis of anthracene. Because anthracene consists of three aromatic benzenoid ring systems, resonance phenomena is exhibited by this molecule. And now coming to the number of resonance structures, as you are aware, the number of resonance structures in case of cyclic molecules, it depends on n+1 formula, where n is the number of rings. The total number of rings in anthracene are 3. So 3 plus 1 means 4 resonance structures are possible for anthracene. And these are the 4 resonance structures for anthracene. Now first let us consider how this first resonance structure can be drawn. So first write 3 hexagon ring systems and link to each other. Okay, that means first you give the carbon skeleton. Okay, then try to adjust the double bonds. So if you consider this as the first ring system, okay, first aromatic ring, second aromatic ring, and third aromatic ring. Okay, so in the first aromatic ring, write similar to the structure of benzene. Okay, that means represent one of the K-class structure of benzene as first aromatic ring. Here, all these polynuclear aromatic hydrocarbons, they consist of conjugated double bonds. So here the thumb rule that we follow is, once there is a double bond at one particular position, we have to leave the adjacent position, okay, as single bond. And next position we can keep double bond. So that is how these two positions we will avoid to keep double bond, and the next two positions we will keep the double bond. So that is how we have to adjust the double bonds even in the third ring system also. So this is how we can draw the first resonance structure in anthracene. Okay, now if you look at the difference between these 4 structures, or how we can make 4 structures, because we know that now 4 resonance structures are possible. Now give 4 anthracene skeletons first. Okay, skeleton means because benzene ring can be represented with hexagon. So give 3 cyclic systems which are fused to each other linearly. Okay. Now try to adjust the double bonds. Now adjusting the double bond, you follow in any one particular criteria. To simplify further, label all the aromatic ring systems as 1, 2, 3 ring systems. Okay. Now try to find out the difference between first and second aromatic ring systems. Okay. So the first and second aromatic ring systems, 2 and 3 aromatic rings were drawn. That means the double bonds which are present in the 2 and 3 aromatic rings were drawn similarly. Okay. Now what is the difference? Difference is there in terms of only the first aromatic ring system. Okay. Now again, what is the difference here? The first aromatic ring system was represented with the help of 2 K-class structures of the benzene. So this is one of the K-class structure of benzene. This is another K-class structure of benzene. Okay. So that is the only difference between resonance structure 1 and 2. Now coming to the third resonance structure. Now try to find out the difference between second and third resonance structures. So here, in terms of the first and third aromatic ring systems, there is no difference between these 2 structures. Okay. Now where the exact difference is present is in terms of the second aromatic ring system. Okay. And how it is different? Here also again, the benzene K-class structures are represented. Okay, say K-class structure 1 is given for second resonance structure. Then K-class structure 2 is represented to represent the second aromatic ring system in case of resonance structure 3. So these two resonance structures, that is resonance structure 2 and 3, they differ in terms of only the second aromatic rings, the double bonds positioning in case of second aromatic rings. Okay, the first and third rings are similar. Now compare the third and fourth aromatic ring systems. So they differ only in terms of the third aromatic ring system. Okay, the first two aromatic ring systems were written similarly. The double bonds which are present in the first two aromatic ring systems were represented similarly. These two structures, they differ only in terms of the third aromatic rings. Okay, again the third aromatic ring system is represented in the form of two K-class structures of benzene. This is one K-class structure and this is another K-class structure of the benzene. So in terms of only third aromatic ring system, there is difference between third and fourth resonance structures. All the three hexagon structures write first linearly. Okay, then try to adjust the double bonds. Now the logic which I explained is, for adjusting the bonds, for writing one first structure to second structure, only change the first aromatic ring system. Okay, first ring system. Okay, now to write the third resonance structure from second, only change the second aromatic ring system, while the other two aromatic rings double bonds will be similar. Okay, now for writing the fourth resonance structure from third, you will be changing only the third aromatic ring system. That means you will represent another K-class structure for the third aromatic ring system. Okay, you can see first aromatic ring, second aromatic ring, third aromatic ring. In this order, you can make changes. Okay, what is the change that we are going to implement is, in one structure, one K-class structure of benzene will be given. Now you represent that particular ring. If it is first ring while for writing second resonance structure. Okay, first ring you represent the another K-class structure for writing the benzene ring. Remaining rings will be similar. Okay, so this is how you can implement so that you can easily write the resonance structures without any mistakes. Now all these four structures can be together represented with the help of a resonance hybrid. So for writing a resonance hybrid also, you can make first three hexagons, combine them linearly. Okay, so that means you are giving the carbon skeleton. Now because all the 14 carbons which are present in anthracene, if you put all these four structures together, it is like all carbons are having double bond character. That is why in each hexagon ring system, draw a circle which is close to that of the carbon skeleton, and that is how we can represent the resonance hybrid structure. Now, when we discuss about resonance structures of these polynuclear aromatic hydrocarbons, the Fry's rule comes into the picture. Now, what is this Fry's rule is, so whenever a molecule consists of many benzenoid ring system, that means in case of polynuclear aromatic hydrocarbons, because they consist of several aromatic ring systems, stability of these ring systems is important. Even though anthracene is having 4 resonance structures, all the resonance structures do not possess same extent of the stability. The stability will vary. Okay, so that depends on the type of the ring systems present in each resonance structure. So whenever a particular aromatic ring system is having 3 double bonds, that means the structure is resembling as that of the benzene. So that is designated as a benzenoid ring system. Okay, which is denoted as B. Okay. Now, on the other hand, whenever an aromatic ring is consists of only 2 double bonds, okay, then it is considered as a quinonoid ring system, which is denoted as Q. Okay, so in case of first resonance structure, the first ring is benzenoid ring, second ring is quinonoid ring, and third ring is also quinonoid ring, because even though all the carbon atoms are having double bond character, but within the ring, if you see, only 2 double bonds are present here. That is why it is a quinonoid ring. So like that, for second resonance structure also, if you see, it consists of 2 benzenoid rings, okay, and 1 quinonoid ring. Now coming to the third resonance structure, it consists of, the first ring is quinonoid and the second and third rings are benzenoid ring systems. Okay, so remember students, here this is the junctional double bond. Okay, and this double bond is belongs to both second aromatic ring and third aromatic ring. Okay, that is why it is considered as that is why here both the rings are considered as the benzenoid rings. Now coming to the fourth resonance structure, it consists of quinonoid and benzenoid rings. Okay, so this is how in each ring, whether it belongs to benzenoid ring system or quinonoid ring system, should be represented. Okay, and now there is a rule which states the stability of these resonance structures, which is known as Fry's rule. According to Fry's rule, the resonance structure which is having more number of benzenoid ring systems is more stable. As we know, benzene is stable molecule because of the resonance phenomena. Okay, so now out of these 4 structures, find out which of the structure is having more number of benzenoid ring systems. Okay. So here two quinonoids, that means here quinonoids are more, here also quinonoids are more. In second resonance structure, here more number of benzenoid rings are present, and even in the third resonance structure also more number of benzenoid rings are present. So according to Fry's rule, structure 2 and structure 3 are considered as stable when compared with the other resonance structures of the anthracene. Now let us consider the stability of anthracene when compared with benzene. The stability of naphthalene when compared with benzene is already discussed in the earlier course videos. So in similar lines, now let us consider the stability of anthracene. So the structures of all three are given here along with their resonance energy. And now in case of anthracene, it consists of three aromatic ring systems, and the resonance energy of all these molecules are mentioned here. So in case of anthracene, the resonance energy is 351.5 kilojoules per mole, where it consists of three aromatic ring systems. Okay. Now we are having the structures, resonance energy, and the number of rings present here. Okay. As discussed under naphthalene course video, for anthracene also we have to consider the resonance energy with respect to each benzene ring. Okay. So for considering that, we have to divide this 351.5 by 3 because it consists of three aromatic ring systems. Okay. Then we will get around 117.17 kilojoules per mole. Okay. That means benzene is having 150.6 kilojoules per mole. Okay. And naphthalene, for with respect to each benzene ring, if you see, it consists of around 227 kilojoules per mole as discussed under the earlier course video. And while for anthracene, with respect to each benzene ring, it is having only 117.17 kilojoules per mole. Okay. And now what is the relationship between the aromaticity or stability with that of resonance energy? If you see, aromaticity is proportional to the resonance energy. That means greater the resonance energy, greater will be the aromaticity, greater will be the stability. Okay. But in case of anthracene, it is having less resonance energy, that is 117.17 kilojoules per mole. Okay. So it is because of this reason anthracene is considered to be less aromatic than benzene. Okay. So lesser the aromaticity, lesser will be the stability, and greater will be the reactivity. And because of this reason, anthracene is more reactive than naphthalene as well as benzene. Aromaticity, so greater the resonance energy, greater the stability, and greater the aromaticity. So based on that stability order for these three molecules, if you see, benzene is more stable because of its higher resonance energy. Okay. And then naphthalene, and then anthracene. That is, among the three, benzene is highly stable and anthracene is the least stable molecule. So I hope the resonance phenomena in anthracene is clear to you from the earlier discussion. So if you have any doubts related to this particular concept, you can type your questions in the chat. And the next topic which I am going to explain is the isomerism in anthracene. So how many different positions are present in the structure of anthracene? Because this particular information, if you know, based on that you can easily predict what type of attack is possible on the electrophilic substitution reactions of the anthracene. So this also will be discussing in a similar way as that of the naphthalene. So if you have any doubts related to the earlier topic, you can type your questions in the chat. So meanwhile, I'll be beginning with the next topic. Structures of anthracene are given along with the positions, different positions. First structure is represented in terms of alpha, beta, gamma, and the second structure is represented in terms of the numerical values. So we can start numbering the aromatic ring systems from this side, okay, as shown here, or as shown in the second structure. We can also even start numbering the aromatic ring systems like this, 1, 2, 3. Okay. Try to relate this isomerism or the different positions present in anthracene with respect to naphthalene, whatever you learned. Okay, so naphthalene consists of only two aromatic ring systems. Those two aromatic ring systems of naphthalene you can consider as 1,3 rings in the structure of anthracene. Okay? Let us consider the rings, 1,3 rings are adjacent to each other. Okay, then it becomes naphthalene. And just recollect how we have numbered the positions in case of naphthalene. Okay, similarly, the numbering or the positions are given with respect to 1,3 rings in case of anthracene. Okay, so these 4 positions are alpha positions and these 4 positions are beta positions. Even the numbering for these two ring systems are also given similar to that of naphthalene. Okay, if you consider this as the first ring system, then first four positions we will give to the first aromatic ring systems. The next four positions, okay, will be giving to the another aromatic ring system. So that is why we have continued here 5, 6, 7, 8. Now the leftover positions in case of the middle ring systems are 9 and then 10. So this is how numbering will be given for the anthracene. So how these alpha and beta positions are given, you can refer back to naphthalene isomerism course video. I have explained it clearly. Now coming to the other different position, that is gamma position. So if you look at the gamma positions which are labeled here, the chemical environment surrounded by this 9th and 10th carbons are similar. Okay, because these two carbons on either side, they are having two aromatic ring systems. So the chemical environment is similar. They are chemically equivalent. That is why to differentiate from the alpha beta positions, it is designated as gamma carbon atoms. So this is how, if you see anthracene, it consists of three different positions. So these three different positions are designated as alpha positions, beta positions and gamma positions. So coming to alpha beta positions, the numbering we have given similar to that of naphthalene. So the same carbons will come. So alpha position is nothing but 1, 4, 5, 8 positions. Now coming to beta position is nothing but 2, 3, 6, 7 positions. Okay. Whatever the leftover positions are there, they are gamma. They are nothing but the 9th position and 10th position in the structure of anthracene. Because anthracene consists of three different positions or three different types of hydrogens, upon electrophilic substitution reaction, there is possibility of formation of three isomeric products, alpha, beta and gamma substituted products. I hope the isomerism phenomena in anthracene is clear to you. So, unlike the naphthalene, in case of naphthalene, two different positions are present, alpha position and beta position. While when it comes to the anthracene, it consists of three different positions. That means anthracene consists of three different hydrogens, alpha, beta and gamma hydrogens. Okay, so this particular information plays a crucial role when we discuss about the electrophilic attack on the anthracene ring system. So if you have any doubts related to the isomerism in anthracene also, you can type your questions in the chat. Alternatively, if you are watching the replay of this particular session, then a WhatsApp group link will be available. So you can join in that group and you can also post your doubts and clarify your doubts at any point of time. Now the next, let us consider about the Haworth synthesis of anthracene. Okay, so if you are watching the replay of this particular session, so first you complete the Haworth synthesis of naphthalene, which I took in earlier session. A replay will be available. So because once you understood how exactly we have conducted the Haworth synthesis of naphthalene, depending on that you can easily understand the Haworth synthesis of anthracene. Now let me share my screen to explain the same. So one of the important method of preparation of anthracene is Haworth synthesis. Now the Haworth synthesis of anthracene is also similar to that of the Haworth synthesis of naphthalene. Okay? So if you have not completed that course video, first complete that course video so that you can easily understand the steps involved in the Haworth synthesis of anthracene. Okay, so if you look at the difference in the Haworth synthesis of naphthalene, in the first step, benzene is allowed to react with succinic anhydride in the presence of aluminum trichloride. Okay. But in the Haworth synthesis of anthracene, the first step is benzene reacts with phthalic anhydride. In case of naphthalene, benzene and succinic anhydride are used as the starting compound. Because naphthalene consists of two aromatic rings, so one of the aromatic ring is obtained from the benzene structure, while the other aromatic ring system is obtained by the cleavage of the succinic anhydride and then followed by cyclization. Now, in case of anthracene, it consists of three aromatic ring systems. So, one of the benzene ring in anthracene can be obtained from benzene itself, okay, while the other two ring systems of anthracene can be obtained by taking phthalic anhydride. So, benzene reacts with phthalic anhydride in the presence of aluminum trichloride. That means it is a Friedel-Crafts acylation reaction. That means the first step is a Friedel-Crafts acylation reaction. Now here also cyclization occurs between the carbonyl carbon and the oxygen of the anhydride ring system. Okay, so this CO group gets attached to the benzene ring system. Okay, so here cleavage occurs, CO group is attached here and then CO group is attached to the aromatic ring system. Okay, so that CO group is here. Okay, now this side the group it becomes CO O. Okay, now this COO of the anhydride it becomes COOH. Okay, and this will be attached to the benzene ring system. Okay, that is how we can link both these ring systems via a carbonyl group. Okay, via a carbonyl group, and that carbonyl group is this carbonyl group where exactly cleavage is happening. Okay, that is how we get corresponding intermediate. Now this intermediate is treated with concentrated sulfuric acid, so the dehydration occurs. During this dehydration, hydroxyl group from the carboxylic group and hydrogen from the benzene ring system is removed in the form of water molecule. Okay, so with the loss of water molecule, so here this carbonyl group gets attached to the benzene ring system, and that is how we will be getting this particular bond, and that is how we get a corresponding tricyclic molecule. Okay, and this tricyclic molecule is nothing but 9,10 anthraquinone. So these are the 9 and 10 positions on the structure of anthracene. So the compound which is obtained is known as 9,10 anthraquinone. Now the structural difference between this anthraquinone with anthracene is, here 9,10 positions carbonyl groups are present, while in case of anthracene it consists of only carbon hydrogen with double bonds. So that means we have to convert this carbonyl group into corresponding hydrocarbon. So this conversion of carbonyl group to corresponding hydrocarbon can be achieved by performing Clemmensen reduction. Okay, that means the resulting 9,10 anthraquinone is treated with zinc amalgam in the presence of hydrochloric acid, so that carbonyl group gets converted to hydrocarbon, and that is how finally we will be getting anthracene. So in this particular Haworth synthesis of anthracene, the first step is Friedel-Crafts acylation reaction, second step is dehydration, and the third step is Clemmensen reduction. So if you feel difficulty in understanding or writing these 3 steps in Haworth synthesis of anthracene, still you can simplify this particular reaction, students. So write only the first step, okay, as I mentioned under naphthalene also. So phthalic anhydride reacts with benzene in the presence of aluminum trichloride, then keep multiple number of arrows, which indicates that it is a multi-step reaction, and directly give the structure of anthracene. Okay, so in this way also you can represent. Okay, and there are other few important methods are also there. So let us consider those methods. So we can conduct Friedel-Crafts reaction also. That is Friedel-Crafts reaction between 2 moles of benzyl chloride. So this is C6H5 benzene ring with CH2Cl group is known as benzyl. This reaction occurs in 2 steps. In the first step, 2 moles of benzyl chloride reacts in the presence of anhydrous aluminium chloride. During this, cyclization of these 2 molecules occurs. So this CH2Cl links here. So chlorine from CH2Cl group and hydrogen from benzene, other benzene ring system. Okay, so will be lost in the form of hydrochloric acid. Okay, similarly this side also chlorine from one benzyl chloride and hydrogen from the other benzyl chloride will be lost in the form of hydrochloride. Okay, now here this is how cyclization occurs between 2 benzyl chloride molecules. So as a result of this cyclization, first we will be getting 9,10 dihydroanthracene. Okay, that means 1,3 aromatic rings are benzene rings, while the middle ring is not aromatic in this particular molecule. Now, in order to get double bonds even in the second aromatic ring system, the hydrogens which are present at 9,10 positions should be removed. That is why in the second step, this 9,10 dihydro derivative is subjected for dehydrogenation, so that double bonds will be introduced even in the second aromatic ring system also, and that is how finally we will get anthracene. Now, the other reaction is known as Fittig reaction. So here also benzyl halide derivatives will be taken. So here 2 moles of ortho-bromo-benzyl bromide. Okay, so if you remove this bromine, okay, this is like the previous molecule structure. Only chlorine is replaced with bromine. That means this is benzyl bromide. Now this benzyl bromide is having bromine ortho to that of CH2Br group, and that is why it is known as ortho-bromo-benzyl bromide. So upon reaction of 2 moles of ortho-bromo-benzyl bromide in the presence of sodium and anhydrous ether, cyclization occurs. So here cyclization occurs as explained in the previous reaction, and that is how all the 3 rings will be fused to each other. But the derivative which we will be getting in the first step is 9,10 dihydroanthracene. So this 9,10 dihydroanthracene, in order to generate double bonds even in the second ring system, hydrogens has to be removed. Okay, that is why oxidation is performed here. Okay, so the double bond will be introduced even in the second aromatic ring system, and that is how finally we get anthracene. Now the other reaction is known as Alps reaction. So in this ortho-methyl benzophenone will be taken. Okay, so without this, this particular structure is known as benzophenone. Okay, now this benzophenone is having methyl group at ortho position of this particular side chain. That is why it is known as ortho-methyl benzophenone. Okay, so this ortho-methyl benzophenone is subjected for pyrolysis, that is heated at elevated temperature, that is between 400 to 450 degrees centigrade. Then cyclization of this molecule and dehydrogenation occurs, and that is how double bonds will be incorporated even in the second ring system, and finally we get anthracene. So these are few important reactions. Among these reactions, at least try to learn the first two reactions. Okay, that is Haworth synthesis and also followed by the Friedel-Crafts reaction, because the first step involved in Haworth synthesis is nothing but the Friedel-Crafts. So the second reaction also becomes very easy to learn. I hope the Haworth synthesis of anthracene and other methods of preparation of anthracene are clear to you. So this Haworth synthesis, at least, okay, out of the methods, whatever I explained, so out of the 4 methods, whatever I explained, at least try to practice and remember Haworth synthesis. That is very, very important. So if you have any doubts related to this synthesis of anthracene also, you can type your questions in the chat. Now, the next topic which I am going to explain is reactions of anthracene. So, similar to naphthalene, anthracene also undergoes 4 types of reactions. Okay. First, let us see what are these 4 different types of reactions, and then I'll be explaining first about electrophilic substitution reactions. So, what type of electrophilic attack is possible? What is the point of attack on the structure of anthracene? Then I'll give few examples. Okay. Now, let me share my screen to explain the same. So the reactions of anthracene are similar to that of naphthalene because both are aromatic compounds. Even the anthracene, it undergoes electrophilic substitution reactions. Further, it will also undergo addition reactions, oxidation and reduction reactions. Now in this particular course video, let us first consider the electrophilic substitution reactions of anthracene. So these electrophilic substitution reactions of anthracene and the point of electrophilic attack on anthracene, you can easily understand provided if you have already learned about the electrophilic substitution reactions of the naphthalene. Okay. So if you have not completed those course videos where I explained about electrophilic substitution reactions of naphthalene and the point of attack on the naphthalene, first complete those course videos, then again come back to this course video so that you can easily understand the reactions in case of anthracene. So why anthracene undergoes electrophilic substitution reaction? The reason is very much similar, students. So you have to mention at least why electrophilic reaction occurs and why substitution reaction occurs as discussed under naphthalene. Okay. So here anthracene, it consists of 7 conjugated double bonds. So due to the availability of 7 pi electrons, anthracene is considered as electron rich molecule and it becomes site for the attack of electrophiles. It is because of this reason among 3 types of the reagents, that is electrophile, nucleophile and free radical, electrophiles will be more prominently attacking on the aromatic ring systems of the anthracene. Even after electrophilic substitution, the rings, they maintain aromaticity. It is because of this reason anthracene undergoes electrophilic substitution reaction similar to that of benzene. That means even in the electrophilic substitution reactions of anthracene, there will be 3 steps, okay? That is electrophile generation, carbocation formation and deprotonation, okay? But because we know that there are 3 different types of hydrogens are present in the structure of anthracene, okay? The incoming electrophile, whether it replaces alpha hydrogen, beta hydrogen or gamma hydrogen, we have to find out. Okay, that means what is the preferred point of attack for the electrophile, whether it is alpha, beta or gamma position. So the point of attack of electrophile on anthracene, it depends on the stability of the resulting carbocation in the rate determining step. That means we have to write the carbocation formation step for all the 3 possible attacks. That is alpha attack, which is nothing but 1 attack, beta attack, nothing but 2nd attack, and gamma position is nothing but the 9th position. Okay, so based on the knowledge that you attained in case of naphthalene reactions, now you can write these 3 attacks. Okay, you can try at least write the structure of the resulting carbocation, how many resonance structures are possible, and the final product also. That is 1 substituted product, 2 substituted product, and 9 substituted product. I hope you might have tried to a little bit. So for your clarity, let me explain this particular attack. Okay. So here you can see anthracene structure is given. So electrophilic attack. So electrophile here is denoted with Y plus. So electrophilic attack on anthracene is shown at 3 possible positions. Okay. So instead of writing alpha attack, I have given it as 1 attack. Okay. So this is alpha attack is nothing but 1. This is beta or 2 attack and this is gamma or 9 attack. Okay. Now let us discuss one by one. Okay. Now when electrophile attacks at first position, okay, it utilizes the double bond which is present between 1 and 2 carbon atoms. Okay. And that is how it will make a bond with the electrophile, that is Y group. Okay. In that case, the carbon which is present at second position becomes electron deficient. That is why a positive sign is shown here. Okay. Now the rest of the molecule structure is given similarly. Okay. Similar to that of the first anthracene structure which is given. This is how there will be formation of a carbocation. Now, another resonance structure is also possible for this carbocation. That is, just shift the double bond which is present in the first aromatic ring system to adjacent position to remove the positive charge from the second position. Okay. In that case, there will be a new double bond formation occurs at second position. But at fourth position, the carbon becomes electron deficient because we are moving the double bond from that position. So keep a positive charge on the fourth carbon atom. And other two aromatic ring systems are written similarly as that of the first resonance structure. And this is how we can get another resonance structure for the resulting carbocation. Like this, you can draw few more resonance structures also by changing the Kekulé structure of the benzene for the remaining aromatic ring systems for the resulting carbocation. Okay, but what is more important is here I simply mention as given that other resonance structures are also possible. Okay, and so on I have given. Okay, here instead of the number of resonance structures, the stability of the resulting carbocation is important. Okay, so if you look at the resonance structure which is obtained in the first attack, here the naphthalene ring system is intact. Okay, so wherever electrophile is attacking on that aromatic ring system, there is disruption of the aromaticity. Okay, while the other two aromatic ring systems are maintained as it is. Okay, and in fact, with respect to other two aromatic ring system, naphthalene structure is maintained. Okay, so in these two resonance structures also same is observed. Okay, that means the resulting carbocation is a derivative of naphthalene. That means when electrophile attacks on first position, the resulting carbocation is a derivative of naphthalene. Okay. And now once the carbocation is formed, immediately it will undergo third step, that is deprotonation, and thus it gives corresponding one substituted anthracene product. Now coming to the second attack, that is when electrophile attacks at the second position. This is the second position. Then it utilizes the double bond electrons which are present at the second position, and it will make a bond with the electrophile. So in that case, the first carbon, it becomes electron deficient, and that is why a positive sign is shown. Okay, so here also few more resonance structures are possible, just shown as and so on. Okay, now here also if you look at the carbocation structure, it is also a derivative of naphthalene because the substitution is happening with respect to the first aromatic ring, which is undergoing disruption during this substitution reaction, but the other two aromatic ring systems are maintained as it is. That means the aromaticity is preserved as it is. In fact, it is looking like naphthalene structure. That is why we consider it as naphthalene derivative. Okay. Now this carbocation also, it will undergo the third deprotonation step. Okay. And it gives corresponding to substituted anthracene. Now when the electrophile attacks on anthracene at 9th position, this is the 9th position, then it utilizes the double bond which is available at the 9th position, and it will make a bond at the 9th position. That is how it is attached to the 9th position. Okay. Now during this attachment, the double bond which is present at 10th position will be migrated to the previous position. When it migrates to the previous position, then only the first ring system, it becomes aromatic because it consists of 3 alternative double bonds. Okay. So in that case, the 10th carbon, it becomes deficient of the electrons. That is why positive charge will be developed on the 10th position. Okay. And that is how it results in the formation of a carbocation. Okay. Now if you look at the resulting carbocation structure, the first and third ring systems are benzenoid ring system. Okay, that means they maintain aromaticity. Okay, wherever the attack is happening, that is on the second ring system, there is disruption of the aromaticity. So upon 9th attack, the resulting carbocation is a derivative of benzene because it consists of two isolated benzenoid ring systems. Okay, and as soon as this particular carbocation is formed, immediately it will undergo deprotonation step, and thus it results in the formation of corresponding 9 substituted anthracene as the product. Now, overall, if you see all these attacks in alpha R1 attack, the resulting carbocation is a naphthalene derivative. Okay. Even in second attack also, the resulting carbocation is a derivative of naphthalene. Okay. Now, when it comes to the gamma R9 attack, the resulting carbocation is a benzene derivative. Okay. Benzene derivatives are highly stable when compared with naphthalene. Gamma R9 attack, the resulting carbocation is highly stable when compared with the carbocations which are formed in first and second attack. It is because of this reason, as soon as the carbocation is formed in gamma attack, it immediately undergo deprotonation step, and it results in the formation of 9 substituted derivative. Okay. So it is because of this reason, gamma attack or 9 attack is more preferred in case of anthracene when compared with 1 and 2 attacks. So that is what is given here. So in 1 and 2 attacks, the resulting carbocation is an naphthalene derivative, while in 9 substitution, it gives carbocation which is having 2 isolated benzene ring system. So benzene stability is more when compared with naphthalene. It is because of this reason, the carbocation which is formed in gamma attack or 9 attack is more stable when compared with the other 2 attacks, that is 1 and 2 attack. Okay, hence the preferred point of attack of electrophile on anthracene ring system would be at gamma position or 9th position. Let us consider few examples for aromatic electrophilic substitution reactions of anthracene. These are the few examples for the aromatic electrophilic substitution reactions of anthracene. So anthracene, when it is subjected for nitration in the presence of concentrated nitric acid and concentrated sulfuric acid, from this reagent, nitronium ion will be generated. So the liberated nitronium ion will be acting as electrophile and it attacks at the 9th position because the preferred point of attack in case of anthracene is at 9 and 10th position. Okay, so both are gamma positions. So once nitro group attacks at 9th position, it results in the formation of 9-nitro-anthracene derivative. When the resulting 9-nitro-anthracene, when it is further subjected for nitration in the presence of same reagent, then here also there will be generation of nitronium ion. Now the formed nitronium ion, it prefers to attack at 10th position because 10th position is also gamma position. Okay, because 9th position is already occupied in the previous step. Now the next incoming electrophile, it prefers to attack at the 10th position. And that is how there will be formation of 9,10-dinitro-anthracene as the product. The second example is a bromination reaction when anthracene is allowed to react with bromine in the presence of carbon tetrachloride. Here also from bromine there will be formation of bromonium ion in the first step of the electrophilic substitution reaction. So this bromonium ion prefers to attack at 9th position, okay, because that is the preferred point of attack, and as a result of which there will be formation of 9-bromoanthracene as the product. Now the third reaction is a type of chloromethylation reaction. In this reaction, anthracene is treated with a mixture containing formaldehyde and hydrochloric acid in the presence of phosphoric acid. So from formaldehyde, CH2 group, and from hydrochloric acid, chlorine. So together CH2Cl group, chloromethyl group, will be attached to the 9th position. And as a result of which there will be formation of 9-chloromethyl-anthracene as the product. So nitration, bromination and chloromethylation of anthracene are the few examples of electrophilic substitution reactions of anthracene where the generated electrophile, it prefers to attack at 9th position. Okay, so other than these reactions also, anthracene undergoes sulfonation and Friedel-Crafts acylation reactions where the point of attack will be little different. Now let us consider those reactions. So the first one is sulfonation reaction. When anthracene is subjected for sulfonation at low temperature by treating it with dilute sulfuric acid, then there will be generation of sulfur trioxide. So the formed sulfur trioxide will be acting as electrophile. Now in case of anthracene sulfonation, the formed sulfur trioxide prefers to attack at first position at low temperature, as a result of which there will be formation of anthracene 1-sulfonic acid as the product. On the other hand, when anthracene is treated with concentrated sulfuric acid at high temperature, that is at 160 degrees, then the formed sulfur trioxide, it attacks at 2 positions. Okay, so that is, it attacks at 2 alpha positions from the 2 different ring systems. So as a result of which we will be getting 2 isomeric products. One is 1,5-disubstituted sulfonic acid derivative. The other one is 1,8-disubstituted sulfonic acid derivative of the anthracene. This is how low temperature favors the sulfonation to occur at first position in case of anthracene, while at high temperature, the incoming electrophile, it prefers to attack at 1 and 5 or 1 and 8 positions. That means overall, if you see, alpha attack is predominant in case of sulfonation reaction. Now the other reaction is Friedel-Crafts acylation reaction. When anthracene is treated with a mixture containing acetyl chloride and aluminum trichloride in the presence of dichloromethylene, the CH2Cl2 is dichloromethylene. Now from the reagent mixture, there will be generation of acetyl cation. Acetyl cations which are formed will be acting as electrophile and they attack at gamma position. Okay, and as a result of which there will be formation of 9-acetyl-anthracene as the product. On the other hand, when the same acetylation reaction is performed in the presence of nitrobenzene as the catalyst, then the generated electrophile, that is acetyl cation, prefers to attack at first position, as a result of which there will be formation of 1-acetyl-anthracene as the product. So this is how the point of electrophilic attack will be different when compared with the usual preferred attack, that is gamma position, when it comes to sulfonation reaction and Friedel-Crafts acylation reactions of the anthracene. So I hope the electrophilic substitution reactions of anthracene are clear to you. So when it comes to the anthracene, the preferred point of attack is at gamma position, that is at 9th position. Okay, and we have considered few examples also. So if you have any doubts related to the electrophilic substitution reaction in terms of point of attack or in examples, you can type your questions in the chat. Okay. So the next topic which I am going to take is other reactions. So in addition to electrophilic substitution reaction, anthracene also undergoes oxidation reduction and addition reactions. No, so let me explain about all those other reactions. But meanwhile, if you have any doubts related to the earlier topic, that is electrophilic substitution reactions, you can keep your questions in the chat. So let me share my screen. The first reaction is addition of oxygen. Anthracene in the presence of air and light, the oxygen present in the air, it attached on the anthracene ring system at 9 and 10th position. So in between this ring system, it will be attached. As a result of addition of oxygen at 9 and 10th positions of anthracene, there will be formation of anthracene 9,10 peroxide as a product. Now, the second addition reaction is dimerization reaction. That means here 2 moles of anthracene, they undergo polymerization reaction. Because 2 molecules are undergoing polymerization, it is known as a dimerization reaction. This reaction occurs in the presence of either benzene or xylene in the presence of light. Basically, all these polymerization reactions are a type of free radical addition reactions. As a result of dimerization, the 2 moles of anthracene, they undergo dimerization, and as a result of which there will be formation of dianthracene. In order to write the structure of dianthracene, write the carbon skeleton of 2 molecules of anthracene first. Okay. Then make the first and third ring systems as the benzene ring system. That means each of these rings should contain 3 double bonds. Okay. So as such, if you see there is no double bond, or on the other hand, there will be 2 junctional double bonds with respect to the second aromatic ring system. Okay. Now attach the 9th positions of both the ring systems and 10th positions of both the ring system. This is how 2 moles of anthracene, they will undergo dimerization reaction, and as a result of which there will be formation of dianthracene as dimer. So these are the 2 examples for the addition reactions of anthracene. Now let us consider the oxidation reactions of anthracene. So anthracene, it will undergo oxidation either in the presence of nitric acid or in the presence of a mixture containing oxygen or vanadium pentoxide, or alternatively we can use sodium dichromate in the presence of concentrated sulfuric acid as the oxidizing agent. Okay, so these are the 3 different examples for the oxidizing agents. So in the presence of any of these agents, anthracene undergo oxidation, and here also again the 9th and 10th double bonds which are present in the second aromatic ring systems will be undergoing oxidation, and as a result of which there will be formation of 9,10 anthraquinone as the product. Coming to the reduction reaction, anthracene undergoes different types of reduction reactions depending on the type of reagents used. So, when it is reduced in the presence of sodium amalgam or sodium in ethanol mixture, then here also the double bonds which are present at 9 and 10th positions will be affected. Okay, one of the double bond will be shifted to the previous position while the other double bond is reduced, and that is how there will be formation of 9,10 dihydroanthracene as the product. On the other hand, when anthracene is heated along with nickel by passing hydrogen gas at 200 to 250 degrees, then the first aromatic ring of the anthracene, that means the double bonds which are present in the first aromatic ring of the anthracene will be reduced, and that is how there will be formation of 1, 2, 3, 4 tetrahydroanthracene as the product. Now this formed partially reduced product can be further subjected for catalytical reduction. So each time that we perform catalytical reduction, one of the remaining hydrogen will be reduced, and that is how a tetrahydroanthracene gives hexahydroanthracene. When it is further subjected for reduction, then it gives octahydroanthracene, and this upon further reduction in the presence of nickel and hydrogen, there will be finally formation of decahydroanthracene as the product. That means out of the 7 double bonds, only 5 double bonds will be undergoing reduction, and finally we get decahydroanthracene as the product. So these are the 2 modal reduction reactions of anthracene. So I hope the other reactions, that is addition, oxidation and reduction reactions of anthracene, are clear to you students. So if you have any doubts related to this topics, then you can type your questions in the chat. So almost we have completed the chemistry of anthracene. So we are left with only structure and uses of anthracene derivatives. Okay. So the next topic, let us finish that also. So let me share my screen. So meanwhile, if you have any doubts related to so far content, whatever I covered, so you can keep your questions in the chat. Let us first consider the uses of anthracene. So this is the structure of anthracene. So anthracene is used for the preparation of anthraquinone. I hope you might have remembered the structure of 9,10 anthraquinone. I have given in some of the reactions of anthracene. You can refer to the earlier course videos for its structure. The importance of anthraquinone is that this 9,10 anthraquinone is used in the manufacturing of dyes and pigments, pulp and paper industry, and also it is useful for the production of laxative type of medicines. So, as a derivative of anthracene, you can even give the structure of anthraquinone and give its use as mentioned here. One of the derivative of anthracene or anthraquinone derivative is 2-amino-9,10 anthraquinone. Now, if you remove this amino group, okay, then the structure it becomes 9,10 anthraquinone. Okay. Now, this amino group is present at second position on the structure of anthraquinone, and that is why it is named as 2-amino-9,10 anthraquinone. This 2-amino-9,10 anthraquinone is used in the preparation of indanthrene dyes, and also it is used in the preparation of paints and enamels. Now the other example for anthracene derivative or the derivative of 9,10 anthraquinone is 1,2 dihydroxy 9,10 anthraquinone. Again, the basic ring system is anthraquinone ring system, okay, which consists of anthracene nucleus. Now this particular molecule is having two hydroxyl groups at 1 and 2 positions. That is why we will mention them in the prefix. So the name is 1,2-dihydroxy 9,10 anthraquinone and its trivial name is alizarin. So this compound is actually known as modern black 11 mixture. You might have studied in the pharmaceutical analysis subject in the titrations. Okay. And this particular alizarin is used as a staining reagent. So these are the few examples for anthracene derivatives and their uses. So I hope the structure and uses of anthracene derivatives is clear to you students. So you may get this as one of the 2 marks question also. Okay, so with this I'll stop today's session here. So with this the chemistry of anthracene is completed. So far whatever the content that I took in today's session, if you have any doubts related to it, you can type your questions in the chat. Alternatively, if you are watching the replay of this session, then WhatsApp group link will be available in the description. You can join in that WhatsApp group and you can clarify your doubts at later stage. Now let me share my screen to show you some of the important questions of from this particular topic, that is from anthracene. So the first question is write the structure and uses of anthracene. This you may get as 2 marks question. Then explain the electrophilic substitution reactions of anthracene for 5 marks. So here you can write the point of attack which can be accounted for 2 marks. Okay, alpha, beta and gamma positions, which attack is preferred. Okay, and then 3 marks is for the examples. Okay, so whatever the examples I have given, out of which you can select any 2 or 3 examples, you can write them without any mistake. So in that way marks division will be there. Okay. Then the whole anthracene, if you want to study, first learn what are the resonance structures, Haworth synthesis, that is one of the method of preparation, and any 3 reactions minimum. Okay, if you want to learn, let us say 2 electrophilic substitution reactions, 1 addition reaction, 1 oxidation and 1 reduction reaction. So overall 6 reactions. So like that you can learn very briefly. Okay, and at least Haworth synthesis, even though I have given several number of synthesis, at least Haworth synthesis and the resonance structures. Okay, and the isomerism phenomena in anthracene I explained so that you can easily understand the point of attack in electrophilic substitution reactions. As such, you may not get question about the isomerism in anthracene or naphthalene or in case of phenanthrene. Okay, so that topic will be discussed usually so that you can easily understand the point of attack when it comes to the electrophilic substitution reaction. Okay, so these are few important model questions, students. So with that, the chemistry of anthracene is completed. So if you have any doubts related to this topic, you can type your questions in the chat. Now, soon after this session, quiz will be enabled to students. So soon after this session, review the concept for about 10 to 15 minutes, then only attempt the quiz. Okay, you can take little time to attempt the quiz, but attempt it in such a way that you will get maximum marks. I have given the questions very easily, provided if you watch this total video and just revise it briefly. Also, you can easily score 10 out of 10. Okay, now in tomorrow's session, that is the last session, I'm going to take the chemistry of phenanthrene. So with that, even the fourth unit will be completed. So by tomorrow, all the 5 units, important questions will be covered from POC-II. Okay. Now let us meet in tomorrow's session. Take